Let's do a quick recap on the Lotka-Volterra equations.
Here they are in this format here, and I'm just going to cycle through them, and you can pause at your leisure. Here's the Prey equations. I want to make sure I highlight the functional response, which you've already been introduced to once. Here's the Predator equation, and the numerical response, which is the piece that converts the encounters between the predators and prey into new predator numbers. The way you analyze, this is a bit of an advanced topic, and you can skip it if you want, but I just want to introduce it to you really quick. The way you analyze the dynamics of these situations is you set up a condition that says, what is the situation where the prey is not growing? The prey is not growing when the rate of change is equal to 0. The dn dt is equal to 0. This is referred to as the prey zero growth isocline. Okay, so you ask yourself, what are the conditions that are such that the prey is not growing, and what happens, and how is that related to other features of this interaction? So the way you can solve this, because you know what dn dt is based on the previous equations, that's all that stuff that has to do with the rate of growth. You can rearrange the components in that equation, and basically you can find that the condition where the predator abundance here, the predator density, is equal to the intrinsic rate of growth divided by that predator efficiency, how good they are at converting, in that encounter. That ratio, if this ratio here meets is the same as the density of predators, that is where the prey is not going to grow. Okay, so here's when the predator abundance hits this ratio, and this ratio is set by R over A. If the predator abundance is above that, the prey population is going to decrease. So here's prey abundance. Look, this looks really different. This is prey abundance versus predator abundance here. Okay, when the predator abundance is below this line, that means the dn dt is going to be positive, and the prey population is going to increase. When the predator abundance is above this line, which is set by these two attributes here, the prey population is going to decrease. Lots of predators, populations decrease up above there. Okay, we can do the same exact analysis to see what are the conditions under which the predator doesn't grow. This is the zero growth isocline for the predators. We'll take that equation, you can rearrange it, and you can solve for n, and what you find is that when the prey population is equal to this ratio, that is the condition that gives you no net growth of the predators. So this is interesting. What determines whether the predator is growing or not is determined by how the prey population is relative to this particular ratio, and vice versa. Whether the prey population is growing is determined by the abundance of the predators right here. Okay, so now we can do an analysis very similar to that last one, that the prey abundance is what sets whether the predators are growing or not. So right here on the line, the population is not going to be growing. If the prey abundance is bigger than this amount, predators are going to be increasing. If the prey abundance is below this line, this point here, then the predator populations are going to be decreasing like that. Again, remember, this is prey abundance versus predator abundance. This is pretty different than you've seen before. This is called an isocline analysis. Okay, so you can actually put both of these two things together, the predator and the prey isocline, and you can say jointly, what are the conditions when I'm over here, under these conditions here, what is happening to the predators and the prey? Well, under this particular zero growth isocline here, there aren't enough predators, and so the prey population is going to decrease. This is the blue line. Below this line here, there are too many predators, okay? Yes, below this line here, there's actually enough population of, below this line here, there are not enough prey, and so the predator population is going to be decreasing right here. Okay, so in this quadrant here, prey population is increasing, predator population is decreasing. right? And you can analyze that for every single quadrant that actually exists. So in here, in this position here, predator is going to be decreasing, but prey is going to be increasing. So the net effect of the both of them is going to be in this direction. In this quadrant here, now we've suddenly changed to the place where there's enough prey around, because we're above this predator zero growth isocline, that the predator populations are going to be increasing. But we're still at a point where there are not that many predators, and so the prey population is also going to be increasing here. So in this quadrant here, you have a situation where both of these populations are going to be increasing. And you can go through and analyze this in each one of the quadrants. And basically what you will find is something that looks like this. That as these populations change, they will suddenly transition from one state to the next, because they've crossed these zero growth isoclines. And so when that happens, suddenly a growing herbivore population, or I'm sorry, a growing prey population is going to suddenly start decreasing right here. And when we cross this line, a suddenly growing predator population is now going to start decreasing, and so on. And these are happening simultaneously. These are happening in response to each other. So let's take a look at what happens over time. Now look, this is different. This says time versus the prey and the predator populations right here. And in red are the predator populations, and in blue are the prey populations. So when we're in quadrant A, right here, prey populations are too low, predators are decreasing, but because there aren't that many predators, the prey population is going to be increasing. So this is the prey population is increasing, and the predator population is decreasing. As soon as we cross that green line up above, now there are enough predators, and now the predator population starts to decrease. Now we're in this, starts to increase. Now we're in this quadrant right here. It starts to go up. But the prey population is still increasing, like this.
As I advance the slides, what you should be able to do is map the quadrant and the position of the populations, and then see how going around that circle would cause this particular cycling.
The reason I'm showing you this is because this suggests that there is coexistence between the predator and the prey. That is, there seems to be boundedness. There seems to be the populations don't go to infinity and they don't go to extinction. And so this is a stable predator-prey type of an interaction. Awesome. This is kind of what we would have expected to see. However, this type of Lotka-Volterra continuous time model has a very odd property. And this property is that when this population is perturbed in some way, imagine you add more predators and more prey to the system, or you decrease the number of predators and the prey, as you may get in this situation here. Suddenly there's a decrease. Maybe there's a density independent factor, like a thunderstorm or something, the populations decrease. What's going to happen in this situation? So the interesting thing about the Lotka-Volterra equations, they show some type of stability, whereas when they are not perturbed, there is a cycling around this particular equilibrium point here. But if perturbed away from this point, there is no tendency to go back to the original. So this is a neutral stability, which is rarely observed in nature, really. And so Lotka-Volterra might not be a great way to actually describe the coupling of two predator and prey populations, because this isn't really what we see when we look in nature. Things either tend to return to a previous equilibrium, or perhaps they're not stable at all to start with. And this idea here is this idea that although there is stability, that this is what's often referred to as a neutrally stable system. It's stable only if it's not perturbed. You know, the populations will cycle as long as there's no external factors that disturb it. When that happens, the equilibrium point you could think of, or the attraction, is somewhere else. It's not back where it used to be. So the concept of stability is really the tendency of the system to return to its previous equilibrium state following a perturbation. So in this situation here, as I said, this is a neutrally stable point. It has no, the way the equations are set up, or the system is set up, it has no way to kind of return back to where it was before. Contrast that with this situation here, where this particular system, let's imagine the system is this ball that's kind of confined by this basin right here. A small perturbation away from this point here will kind of bring it back to the initial starting point. Here we have a system where gravity always pulls on things in the same way. They tend to come at rest at a place where kind of they have minimize their entropy, their energy, and they will return to that starting point.
On the other hand, if you perturb this system far enough so that it gets outside of the control of the system here, then
something else will happen outside of that. So this is referred to as a locally stable equilibrium, but it's not a globally stable one. If you disturb it too far, you've kind of gone outside.
The final example is the one over here on the bottom, where the conditions inside of that system are that no matter what perturbation you have, that little blue ball is going to always return to that point of at the bottom of that cylinder, where nothing you can do will ever have it escape and go into some other state outside of that. This is considered a globally stable equilibrium.